Welcome, everyone. This is the 4th Global Passive House Happy Hour of our 2nd year and episode number 56. Thank you for joining us. I'm Prudence Ferreira, and I'm a proud member of the Passive House Accelerator. We couldn't do all of this without their support and without the support of the folks who sponsor them and all of you. I'm also a senior member of the Carbon Neutral Design Group at BR+A Consulting Engineers, and I lead their Passive House team. And I maybe see a couple new faces. For those of you who are new, we're an inclusive gathering. We welcome everyone, no matter your reason for being here, whether you're an expert or a total newbie. You're in the right place to learn about Passive House and GHG reductions and building science. And happy hump day. I was thinking this week, I had an interview with one of our community members who's a student, graduate student at University of Chicago. And he was asking me all kinds of questions about the beginning of Passive House and how everything has evolved. And he got me thinking how far we have come in a decade. And Passive House Accelerator has got our policy summit coming up. And I'm talking to this fellow on the phone, and I'm thinking about the policies that are coming into place now and the standards that are being created, and the fact that we've got people now that are asking for Passive House that don't really understand what it is, but they know they want it. And I just think about where we were a decade ago when nobody knew anything about it, and we were like banging on the doors just trying to get folks to understand, you know, the smallest little thing and trying to correct misperceptions. So I would like to open our show tonight with just a toast to how far we've come and how fast this is ramping up, guys. It's a crazy ride. So please unmute yourselves and join me in a toast. Here's to how far we've come. It's amazing.
Woo.
Cheers.
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 Mm-hmm. All right. So we've got a great show. Our guest of honor and our teacher for the evening is Oliver Stile. And he's got a Master's of Science in Architecture and Advanced Environmental Studies from the University of East London. He's also a certified Passive House consultant and has been for quite a while, as well as a component certifier. And he is director of Praxis Resilient Buildings, and they specialize in fabric first, performance optimization, thermal envelope design, PHPP energy modeling, and hygrothermal analysis, and also thermodynamic sims with Energy Plus and 2D and 3D thermal bridge calculations. So all the fun stuff. And also HVAC system design and specifications. So he is going to share with us tonight his journey in achieving Passive House airtightness requirements in a retrofit and how he achieved those without putting the building and its occupants at risk due to moisture damage. So we're going to hear about an retrofit of a historic building in Barcelona. Thank you for joining us, Oliver. We're happy to have you.
Thank you, Prudence. Thank you very much. And it's a pleasure to be here with all of you. I've always seen these Passive House Accelerator events announced on different social media, and I think you've always got great topics, and it's a pleasure to be here. So I'm going to try and keep it fun and factual and fast, and I hope we can have time for questions and exchange, which is always the most interesting part. So I understand a lot of you have experience in Passive House and some not. I hope I could share a bit of my experience specifically on this project. So I'm just going to present a project we did a few years ago here in Barcelona, in Spain, which was the Passive House retrofit of a multi-residential building, which was a historic building. So we had certain limitations as to what we could do, and we learned a lot along the way. And I want to just present some of the kind of key points of that. So as many of you will know, the Passive House standard has the Anafit seal, which is the retrofit standard for passive house. So it gives us two kind of routes to achieving certification. One is the demand method, which is kind of based on performance targets. So it's very similar to passive house for new builds. That's based on meeting limiting energy demands. It's a good route if you can insulate externally your building, and it's more demanding. And if it also offers the component method, which is a prescriptive, based on prescriptive targets. So the different building elements have to meet limiting U values. So the component method is quite good for historic buildings or any buildings in which you can't put large amounts of insulation externally on the building. It's not quite as demanding as the demand method, but it's great to have these two kind of options. And then there's the common requirements for both certification routes, of which the key one is the air tightness. So we have to reach 1 air change per hour at a 50 Pascal pressure difference. So that's the one that kind of causes terror in a lot of kind of design teams. So it's a big challenge, obviously, in existing buildings to get to that level of air tightness. But it's clearly it's achievable, and I think given the number of buildings that we have already built and in need of kind of deep energy retrofitting, it's a real really important to try and share these experiences and see where we can find low cost effective solutions for air tightness. So just to put you in a bit of context, in Spain, in terms of air tightness requirements, so passive house new build will need to reach 0.6 air changes per hour. Like I mentioned, retrofit and fit 1, the Spanish building code for more compact building requires 3 air changes per hour, and 50 less compact buildings, 6 air changes per hour. And then existing buildings, this is going to vary a huge amount, but we're talking roughly 10 air changes per hour of air infiltration in existing buildings. So we need to get, you know, a 10-fold improvement, which is quite a challenge. So there's lots of reasons to improve the air tightness of a building as long as you control the ventilation. But I just want to show one of them, which I think is interesting, relating to the stack effect. You know, when you warm air in a building, obviously due to its buoyancy, it rises, and that will cause air infiltration on the lower floors and exfiltration on the upper floors. One of the things that this can cause in non-passive house buildings with lots of air infiltration is the entrance of radon gas, now, which is a carcinogenic gas found naturally in subsoil. This is a really interesting study by Barry McCarron and al., which looked at the concentration of radon gas in a series of completed certified passive houses in Ireland compared to non-passive house buildings. And it was quite interesting because the concentration of radon gas in the passive house houses, both on the ground and on the first floor, was below 40 becquerels per meter cubed, and didn't really vary too much between the ground floor and the upper floor. And the normal houses, you know, had quite a high concentration of radon gas on the lower floors, basically because of that, you know, entrance of air coming in through on the ground floor. So sealing a building up is good in lots of ways, particularly in health terms related to radon gas. So the project I'm going to talk about is a multi-residential retrofit of a historic building built in 1954 in Barcelona. So this was basically a largely solid brick wall, about 29 centimeters thick, with some artificial stone on some of the facades. So we couldn't insulate externally; we had to do everything internally, and solid brick walls, just as solid stone walls, are quite complicated when you're insulating internally, because if they are subject to driving rain from the outside, moisture can be coming in continually due to liquid transport in the brick, and if you insulate a lot on the inside, it can be delicate in terms of moisture control, mold growth, condensation, and so on. So briefly, the air tightness strategy that we applied on the project was for the whole building and per floor. So we had an airtight layer running around the external walls, also on the internal dividing walls, which could connect us to the outside at these points. And although we were going to test the building, the completed building just as one complete zone, we also did air tightness on a floor by floor level for two reasons. One was to reduce acoustic bridging and noise between different flats, and the other was to facilitate preliminary air tightness testing on a floor by floor basis. So this is a great image, I think, by Joseph Little, which shows a little bit some of the complexity of insulating a solid wall. So, of course, if we put insulation on the inside face of a solid wall, be it brick or stone, we're reducing the temperature on the face of that wall because we're insulating it against the indoor heat in the winter. So as we lower its temperature, then the relative humidity rises. And if we include a vapor barrier or a vapor check, we can also limit drying potential to the inside. So the standard rule of, put a vapor barrier in and put lots of insulation has to be kind of looked at quite carefully in these walls, because obviously when it rains, these walls, the material itself acts like a sponge and moisture starts coming in. And if we have a vapor barrier here, we can end up trapping that moisture in there. So one of the things we looked at in this project was, do we want a capillary active vapor open strategy, or do we want a vapor barrier? Do we want a vapor check? Do we want dynamic vapor control? So we looked at various different solutions and came up with one which was suited to the project in question and the local climate. So when looking at moisture control, we can look at materials and they can have different functions. A material can be airtight, it can be air permeable, it can be vapor permeable, or it can be vapor impermeable, and it can be waterproof or not waterproof, and in any combination of those three. So we have a range of materials at our fingertips, which we can use, be it plastic membranes, liquid membranes, gypsum plaster, and so on, which offer different characteristics in that sense. So we did a whole load of modeling for this project with the WUFI dynamic hygrothermal modeling package. I'm just going to present basically three that we kind of distilled because we discovered that using vapor barriers or vapor checks could be counterproductive in this case for this building and in this climate. So this is a simulation run over 10 years showing the relative humidity on the inner face of the existing brick wall with insulation applied. Okay, so this is the relative humidity year after year with peaks here of 90. Ideally, we want to be below 80% to avoid creating an environment where mold growth can occur. And of course, we never want to reach condensation. So this is just internal gypsum plaster on this green line as an airtight layer, but no vapor control. This second blue line shows the same thing, but with the outer face of the brick treated with a water repellent treatment, which I'll talk about in a minute. So quite a good improvement there, peaks of 80% relative humidity because of this water repellent treatment on the outer face of the brick. And then just as a major comparison, what would happen if we put a vapor check on the warm side of the insulation? What we found in the simulations was that in fact, drying potential was reduced a bit and the peak relative humidity was higher. So the solution that we opted for basically was this one. Sorry, wrong, this one. Okay, we went for a capillary active vapor open strategy coupled with a water repellent treatment on the outer face of the brick, which is sometimes called brick cream. I know that historic building specialists, and I'm sure that some of you here tonight, sometimes may question the effectiveness of a solution like this, but this is basically a treatment which is like a Gore-Tex. It reduces by about 90% the water absorption of a brick, but it maintains its vapor permeability. So it's quite interesting for solid walls in historic buildings in which you can only insulate internally, which are exposed to driving rain. Yeah, so it stops the amount of water getting in through liquid transport, but it means that the wall can still release water vapor. So of course, a lot of this analysis is really dependent on climate. This is just quickly a profile of the temperatures we have in Barcelona. It doesn't really get very cold. When it gets to about 0 degrees here in Barcelona, everything just sort of stops and people start burning their furniture to stay warm and stuff. Whereas in New York, you get down to -15 and everybody's still kind of happy. So this is quite different different climates which need different solutions. So one of the main things we need to look at if we're using internal insulation on solid walls is the driving rain. So this is the climate file for Barcelona, which shows 500 mil a year of rain, whereas in New York, almost double that. So any wall, for example, which is going to be facing northeast or east in New York, is going to be subject potentially to lots of driving rain. So those are the ones we need to be particularly careful with and look at that in design phase. So just to summarize quickly, what we found was that internal insulation of solid walls is tricky. You need to look at each one as a case-by-case basis. There's no one size kind of fits all. Clearly in cool temperate climates, a lot of the climates that you have in North America, internal vapor checks and or vapor barriers are often going to be needed, but it's important that they don't also reduce the drying potential to the inside of a solid wall, be it brick or stone. So important to look at each enclosure on a project-by-project basis. If possible, measure the water absorption of your existing wall, be it solid bricks or stone, and look at the robustness of your solution with transit tools, if possible, Woofy, Delphin, and so on. The Glazer method, the simplified method for condensation analysis is probably far too simplified in the case of these kind of solid walls with internal insulation. So, and of course, it's always good to be able to monitor performance and learn and improve along the way. So the air tightness strategy we applied in this project was just, as I said, very simple. Gypsum plaster applied on the inner face of the existing brick wall. The ground floor, we had a liquid membrane sprayed onto the terrazzo floors, and the join was with airtight paint. On intermediate floors, we also applied the liquid membrane on the floors and then the gypsum plaster on the walls. Insulation was sprayed cellulose between galvanized steel profiles and plasterboard. The profiles were brought in from the wall slightly to avoid thermal bridging and make sure the insulation could get in there. And then we had foam glass insulation on the floors. So there was already some existing plaster on the inner face of the brick walls that was all cleaned off and then replastered. So it was a solution that the local tradespeople knew well, and it was applied at reasonable cost. And we also did all of the internal walls as well to avoid any leaks going through to the outside walls. This is some images of the liquid membrane on the ground floor and intermediate floors. Given the results that we got on the blower door test, we could have probably done without the liquid membrane on the intermediate floors. And some cost savings would have been possible there, but this is a solution we applied, which then was just sprayed on the joint with the walls to seal them. Surface penetrations, of course, were also sealed with plaster and airtight paint. This is a kind of picture of how not to do surface penetrations of lots of pipes. Ideally you want to separate them, get enough space to get in there with tapes or with airtight paint. Unfortunately, here we couldn't because there was literally no other way we could get all of these pipes in. So they actually, behind the render that you can see there, all of the pipes came through a pre-cut polystyrene XPS board, which was previously sealed. So anyway, we had to keep on top of all of the service penetrations, cables for the motors of the blinds as well. And there you go. So this is just a few images of the insulation system, which was sprayed cellulose internally, which is an interesting solution because you get a homogeneous, complete covering layer of insulation. Important to do it in the summertime or the warmer months because obviously there's quite a lot of liquid in the cellulose once it's applied. If you then seal everything up in the winter when it's all wet, you could have a few moisture problems. So recommendable to do this in the warmer months if possible. The windows, we had them factory, we had the blind casings fixed to the window frames in the factory, and they were delivered on site like this. So the window frames and the blind casings were all delivered on site together, which was a great solution because it just saves lots of headaches in terms of air tightness through these blind casings, which is essential in warm climates, you know, to have some shading. The windows were fixed with metal steel brackets to the inner face of the wall, airtight tapes, and of course the windows were basically installed in the insulation layer to the inside, so reducing the thermal bridge installation coefficient. So here you can see a kind of wood fiber and polyurethane board to hold sit the window on. These steel brackets obviously point thermal bridges, but a good solution, and the airtight tape here taped to the gypsum plaster. So the airtight tape was put on before the brackets and then fixed to the wall and taped. Important to get some primer on the walls before you tape so that everything sticks nice and well. So we did the air tightness testing on all of the upper three floors of the building. Here you can see some of the smoke coming in from the handheld smoke generator. So there was a bit of leakage through the window seals here, you know, but really it wasn't significant because the results were very good. But one of the great things about this famous blower door test is that you can really see what's happening, and in the preliminary test with the smoke, you can correct things if need be. And I think it's a great way for everybody, trades, project design people, to sort of understand what the scope of the challenges and what works and what doesn't. So here's a few images of the blower door machine, which many of you will probably have already seen. You know, it's a machine that pressurizes or depressurizes the building. It means you can measure the amount of air coming in and coming out. We had a couple of guys hanging out the windows with the smoke generators. And the results were really good. On the first floor, we got 0.36 air changes per hour at 50 pascals, so quite far below the requirement for passive house. New build, 0.31 on the second floor and 0.47 on the third floor. A few more leaks to the roof. So really good results, sort of well below the limit for passive house retrofit. And just finally, a quick look at what the impact of air infiltration is on the energy consumption of this building. So these are modeled energy consumption for heating, cooling, hot water, and electricity of the existing building with 10 air changes per hour. And then the energy demands if we reduce air tightness to 0.6. So 37% savings just because of air tightness in the Barcelona climate. So clearly, if you're in northern Canada, those savings are going to be far greater. You know, in Barcelona, we don't have very harsh winters. In euros, at an electricity cost of 19 cents per kilowatt hour, the savings for this building is in the region of 9,000 euros a year for the whole building. So even in the Barcelona climate, reducing air tightness to passive house levels has an economic rationale. And of course, many more important ones to do with health, comfort, reduction in pathologies and moisture problems and so on. So that's pretty much it. Thanks a lot for your time. Here's my contact details, and I hope we can have some questions and discussion.
Fantastic. Thank you so much, Oliver. And we know that it's really late for you, so stick around as long as you would like to, and we'll be thankful for any of your time.
Great. I would happily stay around for a bit. I'll need to get some sleep at some point, but
okay.
Yeah.
Well, let's dive into the questions, Oliver. I guess first one is, how many cups of coffee have you had in the last hour or so?
So I think there's number 2.
All right, that's pretty good. First one, we're gonna head over to Cameron Duncan. Cameron?
Oliver, thank you for the presentation. It's very good. I have sort of a side question, because in my area, we have historic buildings that people keep adding on to. So my question was, with Passive House, do you have a hybrid? Do you have if you're building a new addition and you have a existing historic property, do you do interfit on the existing and a separate standard PHI for the new work?
I mean, I think I think it's possible probably to do a variety of different things. I mean, if you have the certification criteria, the PHI certification criteria is that if you have an existing building which has part retrofit, then I think you probably can do the whole thing according to ANAFIT retrofit. I think it just depends a little bit on each specific project, but I think one of the most important things is that that it's possible to have an exemption based on the kind of building and the limitations that it has. So obviously, historic buildings, you're not going to be able to do certain things that you could on a new build, and that will kind of dictate the kind of the route that you can go. So I don't know if that answers your question very well, but I mean, I think the basic underlying rule, the underlying concept, I think, for retrofit of Passive House is that it has to be the whole building. So you can't retrofit one part of an existing building and get a certification, at least from the PHI. What you can do, though, I think, is get you could do a step-by-step retrofit. You can have a pre-certification of one part of a building. So yeah, I mean, I think the bottom line is, you need to really do a whole building, and if that's not possible, then you can do a step-by-step retrofit.
Okay, well, hopefully I'll find out.
Okay.
Thanks, Cameron.
One in the works. Thanks.
Excellent. All right, Jeff, you have a whole bunch of questions. Why don't you pick one, and we'll come back to you afterwards.
Oh my gosh, I have to pick.
Yes.
Well, I guess I'll combine two of them into one, which is I was curious about the age of the building and how many renovations it has undergone over its lifetime, and if that either simplified or complicated things.
It's a good question. I mean, I think from what I remember and what I understand, the building was renovated once. It was originally built, then it was turned into a school, and then when we got to the project, that was a kind of the second renovation. So it's not especially old building. It was built in 1954, but I think it had been retrofitted once previous to this one. Yeah.
Did that complicate things, you think, or was it? Did it help, or?
I mean, I think it wasn't really it wasn't really an issue one way or the other, because everything was stripped internally. There was a lot of structural work redone. reinforcement of structure and so on. So, um, what had been done previously didn't sort of change things too much in terms of what was done. I mean, I think the question is always with retrofit. How much can you leave there and make the most of to reduce costs? And the environmental impact of the project. But with retrofit, you start scratching away, and then you find all kinds of things which you didn't think were there. Then you've got to be careful and obviously make sure that the end result is going to be a lasting solution. I mean, I think one of the things that I've learned from all of this passive house retrofit is that NFIT provides a really good roadmap for retrofitting buildings, because there's a lot of there's possibility to do a lot of things in the wrong combinations and leading to really bad results. For example, if you change windows in a building, existing building, you without doing anything to the ventilation system, you can rapidly get a call from your client saying, I've got condensation everywhere, because obviously you change the windows, you reduce the air leaks, and if you haven't compensated that with a ventilation system, then you can generate problems. So that the NFIT approach is good because it's systematic and it's holistic. You have to take everything into account, and it's a good way of making sure that retrofits are safe and free from moisture damage. And of course, one of the great things about passive house community like here is there's lots of sharing of information, and lots of people who can get together, have happy hours, and geek out on lots of different technical solutions and share that information, which I think is great.
Thank you very much. It was great, and it was wonderful having you in the breakout group.
Great, thank you.
All right, Jeff, I'll put you back at the end of the line. And that was very crafty what you did with those two questions. I will allow it. It's nice work. Over to Joe.
Hey, yeah, thanks, Oliver, for a really interesting presentation. I don't know if you saw everybody kind of lean in when you started mentioning brick cream, and it's like a bunch of questions about that. So I don't know, would you be able to just speak a little bit more to the decision to use that, and maybe how it measured up economically versus just the reality of what you had the space for on the project?
Sure. It's a great question, Joe. I mean, we looked at this this solution. I don't know the detailed technical, chemical, physical properties of the product, other than what I basically described. It's interesting because it will basically maintain vapor permeability, but it will reduce water coming in through the brick. There's issues, of course. It has a useful working life. So it depends on which manufacturer, which product, and who you talk to, but that may be 15, 20 years. So, in theory, you would need to reapply it 20 years further ahead for it to be effective. Having said that, if you apply it when you retrofit, then at least you're going to protect your building in the first few years where there's more moisture in the building anyway, because you've just built it, and all of the wet materials, plaster, gypsum, mortar, concrete is still drying. So it's going to give you protection in the most sort of critical period. It didn't change the physical appearance of the bricks much at all, because it's transparent. Obviously, if you apply it to one brick and then next to it you don't apply anything, you will notice a slight difference, but it doesn't change the aesthetics of the brick at all. The cost, I can't actually remember, but I think it was in the region of 30 euros a square meter, if I remember rightly. So it was an expense, but it was given the analysis and the simulation results, we advise our client that it was a good solution. So I mean, I think it's a really interesting product for these kinds of walls that you can't render on. You can't put a rain screen. You can't protect them from the driving rain. I don't know if it's common in the US, but it's something that's being used here increasingly in retrofit, and I think it's quite interesting because you've got this problem that these materials are sponges. They take up water, and that water wants to go in, and then you have also moisture from the inside of the building trying to go out, you know, so that can help.
Great, thank you.
Welcome.
Yeah, Oliver, that was a pretty lively part of your discussion. Might be a few more questions, and you might have answered a few more. So we'll see how this goes. Over to Jess Brooks.
Hey, loved your presentation. I'm just getting into Passive House, and I'm particularly interested in preservation. So I'm curious when you mentioned that preservationists may not be interested in this as a technique, and I'm curious as to why there might be some hesitancy. Is it just the fact that there's a cost associated with it down the road in 20 years, or if it's like degrading? That's not, yeah, you know what I'm saying?
Yeah. Yeah, thanks, Jess. I mean, it's just, I mean, you know, it's kind of hearsay. I haven't actually had an active discussion directly with too many historic building experts, but I have just read a few reservations. I think basically on the basis of the fact, not economic, you know, reasons, but just that some questions about whether it affects the vapor permeability of a brick, which for historic building reasons obviously is important to maintain. Because if you put a vapor, if you reduce the vapor permeability of the outer face of a brick, you can be creating more moisture problems. So, so I think that's what I understand to be the only sort of issue there. But also my understanding is that these products will only reduce or they will only increase the water vapor resistance factor by about 10%. But they will reduce the water absorption by about 90%. You know, so it's like having your boots, you know, your hiking boots, which when you get them from the shop, it's great and the water doesn't come in. And then after about a year, you know, you start getting water coming in, and then you can buy the spray, the Gore-Tex spray, which is a siloxane-based thing, the same as this, and you spray it on your boots, and then the water doesn't come in again. So it's that kind of concept. But you know, I think my conclusion that it's safe for use on historic buildings, but I think it's always good to contrast that with experts, of which I'm not an expert on specific historic buildings. Yeah.
Thank you so much.
Okay.
Excellent. And now we're heading over to Devin.
Hi, Oliver. Thank you so much. That was an amazing presentation and awesome work. I was curious, you know, regarding the porosity of the building initially. Was that measured in some way, or how do you do? That was my question.
Great, yeah, great question, Devin. No, we didn't measure the porosity of the bricks. We would like to have done that, but for various mainly economic reasons, the client didn't want to go ahead with it. What we did was we modeled different bricks that have been classified in the WUFI database and other databases. So obviously every brick's a world in itself, especially historic bricks. You know, they can be very different in terms of their water absorption, their thermal conductivity, their heat capacity, their density, and so on.
And if you were to measure it, what would you use? What type of measurement would you like to use? Like
Cast-in tubes, yeah, cast-in tubes. I mean, I haven't actually ever done that measurement myself, but I understand, you know, cast-in tubes inserted into the wall at different points to measure the water absorption rate.
Like a Rylum tube, kind of with a little, like a Rylum tube.
Exactly.
I was under the impression that, I mean, at least if I may, and I don't know what validity this has, but I think it's the American Concrete Institute or Association. They kind of didn't so much think the Rylum tube was so good because so many points would be needed over the face of it because it varies so greatly. But I really appreciate it. And I'm curious about what product did you use, that siloxane based product? What was that?
We used Mapei Antipluvial. Mapei is the manufacturer, and Antipluvial.
And is there a space between the outer Y of the brick, and is there an interstitial space of any sort, or is it all solid masonry?
All solid masonry, yes. Yeah.
Cool.
Solid masonry.
Amazing work. Thank you very much.
Thank you so much, Devin. Thank you. Yeah, no, really good point about the measurement. It's like when you start to monitor a building, it's like, you know, where do you monitor? Where are the sensors? What temperature is it picking up and so on? So you need to, you know, it's clearly an issue about that. But I mean, my conclusion would be it's great to measure something and then have some data and then contrast it with your models, and just remember that all models are wrong. And some
I'm going to ask you one real quick one. If you had to do over again, would you do anything differently?
If we have to do what, sorry?
If you did have to do over again, might you consider doing anything differently?
Good question. I don't think so, except that I would probably not have put the liquid membrane on the intermediate floors to save a bit of money, because that's 20 euros a square meter, and we didn't really need that in the end. Otherwise, I think we would have pretty much done it the same. Yeah.
Awesome. Thank you again.
Thanks,
Okay.
Devin. And over to you, Mark.
Thank you, Oliver. On the interior, after we get past the brick, there were some photos showing the stud base filled with the cellulose. I didn't catch behind the studs. Was there an insulating barrier there as well?
Yes. Well, we just brought the studs in slightly from the outer wall so that the sprayed cellulose insulation could get in there. Okay,
So the cellulose came behind the stud.
Yeah, so the insulation got behind the stud and just, it wasn't a huge thickness in most cases, 2 or 3 centimeters, but just to make sure that we had at least a continuity of insulation there, and not a break with a steel stud, which obviously is a thermal problem. So that was it. Yeah, we just brought the studs in and got a bit of insulation in behind. We didn't have a big thickness, it was 5 to 7 centimeters, which is not a lot in passive house terms at all.
That's what I was going to ask. Roughly, what is the break between the masonry and the stud then at that point for the cellulose?
It varied a bit because none of the walls are straight, but 2 or 3 centimeters. Yeah, 2 or 3 centimeters. So, I mean, the good thing about the component method with retrofit in passive house is that, at least in the Barcelona climate, I don't know what it is, probably more in your kind of climates, but you can put 5 centimeters of insulation, and you can comply with the requirements. It might be 7 or 8 centimeters where you are, but it's not a huge amount, and that's specifically for a reason, because the Passive House Institute have been looking at this problem, and throwing a lot of insulation on an internal wall, on the interface of a solid wall, can be a problem. So it's good, but yeah, it wasn't a huge amount. It was 5 to 7 centimeters.
I have 4 more questions, but I will stop there, and I appreciate the response. Thank you, Sean.
Yeah, you will, Mark. You'll start right now, mister. Zach, over to you, buddy.
All right, thanks. Oliver, this has been fantastic, really inspiring work. Thank you.
Right.
I have a couple of announcements about what's coming up next week. Before I do that, I want to thank our sponsors for making all of this happen. So thank you to our founding sponsors, 475 High Performance Building Supply, Baxtingui Architects, Glavel Foam Glass Gravel, Minutair All-in-One HVAC and Dehumidification, Mitsubishi Electric Train HVAC US, Partel, RDH Building Science, Stocorp, and Zola Windows. Our stakeholder partner is NYSERDA, and our patron sponsors are Aero Barrier, BR+A Consulting Engineers, Brennan Insulation and Airtightness, Inotech Windows and Doors, and US Engineered Wood T-Stud. So thank you to all of our sponsors, and a big shout out again to Stocorp for being our sponsor of the week.